So let me define Cartesian product. If A and B are sets, then the set A cross B, known as the Cartesian product of A and B, is just the set of ordered pairs A, B, such that A is in A and little b is in B. R squared is just like R multiplying itself. And we can see that's the notation for the Cartesian product. And what are elements in that? Well, it's ordered pairs where this X comes from R and this Y, let's use red, comes from this R. Now, so you just have ordered pairs of real numbers, but sometimes those two sets are not the same. So let's let A equal to 0, 1, 2, 3, and B equal to 2, 3, 4. Then A cross B is, well, we have 12 ordered pairs here because there's 4 elements in A and there's 3 elements in B. So if we take every ordered pair containing first an element in A, then an element in B, you see what we get. 0, 2, 0, 3, 0, 4. Then starting with the 1, 1, 2, 1, 3, 1, 4, 2, 2, 2, 3, 2, 4, 3, 2, 3, 3, 3, 4. Now, on your own, this is a good example here. You should probably try this because it'll help sort of elucidate some of those relationships I was talking about earlier. Now, if we're going to talk about A and B on the previous page, which I will go back to, you should try to write out the sets B cross A. It's not the same as A cross B. Number 2, A cross B union B cross A. And then the intersection, which is a little more important in this case, what is contained both within A cross B and B cross A. Finally, do the difference between A cross B and B cross A. See if you can come up with some sort of relationship that connects these 4 sets. We're going to end this video with the final important set definition, which is the power set of A. It's denoted by a script P of A. It's the set containing all subsets of A. And as a quick example, you see that if A has just little a, b, and c in it, the power set of A has the singleton, that means one element, the singleton set A, the set containing only B, the set containing only C, the set containing both A and B, both A and C, both B and C, and finally the set containing all 3 elements, which is just A, and the set containing no elements, which is just the null set. Note that the elements in the power set are sets themselves. Okay, don't write them any other way. These are subsets of A. So they're sets in and of themselves. And I make a little note here that if A is finite, the power set of A is finite. And if A is infinite, then the power set of A is infinite. We'd like to figure out the relationship between the number of elements in A and the number of elements in the power set of A. So let's see. So I'm going to start with an empty set and then fill it up. And how am I going to do that? Well, I'm going to look at the quote unquote first element of A, which we're just going to say is little a. And we might ask, well, is little a in this arbitrary subset of big A? And the answer to that is either yes or no. Now that's depicted by the little 1 over here, this part of the diagram. Let me just separate everything above this green line right here. So you can see if you start with nothing and A is in the set, and we decide that A is in the set, well, then we have the set containing A. If we decide that A is not in the set, then we still have the empty set over here. So answering this question, yes, gives us A. Answering it no still gives us the empty set. Now, once we have that, we might ask, well, is B in the same arbitrary subset? If B is in the same arbitrary subset that contains A, we have A and B. If B is not in the subset containing only A, then we have A without B. But earlier, we might have chosen for A not to be in the subset. If B is in that subset, we get B by itself. If B is not in that subset, we get a set containing neither A nor B, which is the empty set. Now we could do the same for number 3, which is the element C. For each of these 4 sets, we ask, is C in that set? If C is in this set to the left, we get all of A. If C is not, we simply get AB. And we take this down the line until we see every possible subset. You can see here that this is every subset that we have inside our set notation over here. You can see here that there's 2 choices every time we ask if an element is in a subset. So it should be no coincidence or surprise maybe that if A contains n elements, then the power set of A contains 2 to the n elements. We have 2 choices for the first element, 2 choices for the second element, and so on. That's 2 times 2 times 2 times 2, n times for the number of choices. And since each one represents its own subset of A, we get 2 to the n elements.